Hi kids, time for some more rules. This time we are going to do the product rule. So just as a memory refresher from last video, we learned that the derivative of a sum or difference is simply the sum or difference of the derivatives. And that's super handy. But for the product rule of derivatives, which is not like the product or the quotient rule of limits, right? The product rule for derivatives, it's really important that you know what it is not. This is true. This statement is not true. It is not true that the derivative of a product is the product of the derivatives. And that goes for quotient as well. The derivative of a product or quotient is not the product or quotient of the derivatives. It is simply not true. And why it's not true is if you have to remember what derivatives do for you. Derivatives give you a slope on another function, right? So I have the function x squared. The expression 2x tells me about the slopes on x squared at every x. Here's what the product rule looks like. You should write it down, but you should not bother to remember it in this form. I'm going to give you a little bit cleaner form by multiplying that equation through by dx, but you should write it down and think about what it is saying. The derivative of a product of two functions. There's the first function, there's the second function. And because multiplication is commutative, it matters not which order, right? The derivative of product is a sum of two products. The sum of two products. And again, both multiplication and addition are commutative. So it doesn't matter the order that you multiply these two in or which product you add, how the order in which you add. But it is really, really important that you know that it is the derivative of a product is not just the product of the two derivatives. So here's a little bit cleaner version. That's still not how I remember it, though. I remember the derivative of a product of two functions. The first one and the second one is the first function, copy and pasted, times the derivative of the second, plus the second function, times the derivative of the first. That's how I remember it. So here is an example, but I want to, at the same time as doing an example of the product rule, I also want to demonstrate the thinking you should do before the product rule. So step one is that you recognize you have a product, right? That's number one. I have a product. AP will not follow your work if you have a product and you just simply take the derivative of each one and multiply them together. You will not get any follow-through points. That's called an egregious mathematical error. That's their words, not mine. So step one is recognize you have a product. Step two is a thinking step. Should I do algebra or calculus first? So I'm actually going to do this problem with algebra first, because this product, I know how to unproduct that, right? Hello, I've been distributing binomials for a long time. Multiplied them together, combined the like terms, and now I'm going to do calculus. In this case, I chose to do algebra first. Then calculus. And notice that now I can just use my nice derivative of a sum. The derivative of a sum is just the sum of the derivatives, power down. Notice that this was an x to the fifth, so I expect my derivative to be an x to the fourth. But of course, the intent of this lesson is to teach you the product rule. So what if I had instead chose to do calculus first? So if I had done calculus first, I would follow the product rule. Copy down the first function. U is the first function. Then take the derivative of the second function, power down. Then add the second function, just copy it over, multiplied by the derivative of the first function. So notice I did calculus first. Now I have to do algebra because I have to, that answer is not a multiple choice. I've got to clean that up. I've got to go ahead and distribute everybody, which is 6 terms, find the like ones to combine, and shocker, I get the same thing, right? A better, right? They are the same. You are going to be tested on your decision-making process. In this case, I think doing algebra was faster, so I could use the easier rule, right? The product rule isn't devastating, but here with all these, right? And there's an ample opportunity for me to make a silly mistake here too when I've got to distribute so many times, right? But once again, I do recognize that even up here, I recognize I've got an x to the fifth. My derivative should be an x to the fourth. Now, if you have your calculator, if you would go get it, because I want to demonstrate 2 things with your calculator. First, right, why does the product rule have to be what the product rule is? Why can't it just be, if I have a derivative of a product, why can't I just take the separate derivatives and multiply them together? Well, hopefully you can see here that even if you did such a thing, you would end up with an x cubed. And an x cubed cannot possibly describe the slopes on an x to the fifth. We've already determined that, right? An x to the fifth, excuse my dog, if you can hear him growling over there. An x to the fifth looks something like this, right? Look at those slopes, right? Or even an x to the fifth might look something like that, right? This x cubed does not describe all of these slopes. So as much as I'd like it to be so, it's not. And I want to use your calculator to prove it to you. But it's not just to prove it to you. So I encourage you, if you haven't, if you're just like, man, just watch her, there are some keystrokes I'm going to demonstrate with this that you're going to want to get comfortable with. All right, so into y1, I have the original function. I already know what that looks like. It's some kind of 5th degree. Now, in y2, I'm going to type in what its derivative is. So actually, I'm going to turn the first equation off. It's a 5th degree with, I know what its end behavior looks like. I don't need to look at that graph. But I'm going to look at the graph of the derivative. 10x to the 4th plus 33x squared plus 15. Now that's a y-intercept of 15, so I can't just graph in a normal window, right? I'm going to have to at least take this y max up to 15, so I might as well take it to 25 since the bottom is at 15. With a leading coefficient of 10, this thing is going to be pretty narrow, so I think I'll just shrink my x-min and my x-max to 5. And now I'm going to hit graph. Now notice that I do get an x to the 4th. I see what the end behavior is. End behavior is positive with the leading coefficient that was positive, and I have a y-intercept there at 15, right? But here's something. Now remember, to get this rule, I had to do the product rule, or I had to do algebra. If you have a calculator in your hand and you don't need the derivative rule, you just need the graph of the derivative, let me show you a neat little trick here. Hit Math 8. I want the calculator to find the derivative with respect to x of the function I have in y1. And I don't want that derivative at x equals 0, and I don't want the derivative at x equals 2, and I don't want the derivative at x equals -2. I want the derivative with respect to x of the fifth degree function in y1 with respect to every x that's on the calculator screen. Now, I'm going to graph this with a darker line, and this way I can prove that the rule I found in the first one, 10x to the fourth, is the right derivative. I did it right, and my calculator can show me that. Now notice it takes the calculator a little bit of time to calculate the derivative at every point and then plot it, but boom, there it is, mic drop, right? There's my table. Look at my rule. There's my rule in y2. For every x, there's the derivative. And y3 is the calculator getting it for me, right? They get the exact same thing. So I can use my calculator to check to see whether I've got the right one. But there are many times on a calculator portion of the exam where I don't actually need the calculator rule. I just need the graph of the derivative. And knowing this key sequence of getting the calculator to graph the derivative for you during an assessment is a really nice trick, really nice tool that I can use. And AP expects you to use that. So again, what if I had thought the actual derivative was, instead of thinking the derivative was using the product rule, what if I thought the derivative was just, what did I say? 2x times 6x squared plus 5? What if I thought that was the derivative? If I thought that was the derivative and then I let the calculator graph the derivative for me, look at when I check my work. I see the real derivative because the calculator is calculating the derivative at every point and then plotting it. And then I see what I think is the derivative. I'm wrong, right? So don't forget what the derivative gives you. The derivative gives you the slopes of the tangents on that fifth degree polynomial. And this x to the fourth is the actual derivative function using the product rule. All right. Now, if we had the product rule, you know you need the quotient rule. Bam, there it is. Gasp. Oh no, dagger, right? I know it looks heinous. Let's pick it apart, copy it down. Notice that the derivative of a quotient is itself a quotient. I am not afraid of the quotient rule. I know the quotient rule. I've used it plenty of times, but let me tell you that step one is seeing the quotient. And just like the product rule, but sometimes even more important, think, do I have to use the quotient rule? Can I unquotient first? Right? Those are my decision-making processes. Here's me writing without the dx's. I've just gotten rid of the dx's. I think of this as the top, u is the top function, v is the bottom function. So I think bottom function times the derivative of the top minus the top function times the derivative of the bottom, all over the bottom function squared. Now notice the product rule had products and sums in it, and the quotient rule has quotients and differences in it, and they are not commutative, so order matters. Now, if you, just like the product rule, if you do not see the quotient, or you see the quotient and you take the derivative of the numerator and the derivative of the denominator and say, that is my quotient rule, that is the derivative rule, no follow-through points. I don't care how fancy your math is after that, no follow-through points. But if you set up the quotient rule properly, and then you make some silly error with distribution or order, you will get follow-through points. So it's very important to show your work. Again, notice this is not just the quotient of the two derivatives. You will not get follow-through points if that's how you attack this problem. So, bam, there it is. The derivative, right? You're taking the derivative of a quotient. You cannot just take the derivative of the numerator and the derivative of the denominator. You must do the quotient rule. There is no algebra I can do to get me out of this quotient, right? Don't you dare start canceling x's and tell me anything like you cannot undo that quotient. So I must do the quotient rule. I actually do this first. I take the bottom, I copy it over, square it, and put it in a denominator. Then I write the minus sign and I put brackets here so I don't forget to distribute the minus. Then I say the bottom times the derivative of the top minus the top times the derivative of the bottom. On a rubric, if this is not multiple choice, there has to be rubric points for doing the quotient rule. And then I will clean that up a little bit. I will not square out this denominator. I will multiply and distribute the negative and combine what I can, but that's it. And you know what? If I'm actually on a test or a quiz of ours, or even on the AP, I'll yield a simplification point to make sure I finish. I've done the quotient rule. I've demonstrated what I know about the quotient rule. I've used it properly. I've checked that. I'm worried about time for a longer problem. I move on, and then I'll come back and clean this up if I have time. The most I will do is multiply and combine, right? That's it, a bit. Now, I have a mnemonic device for you for the quotient rule. Don't tell Mr. Davis, he hates it. So one year when we were teaching this together and he had a planning period or he was going to teach, but it was not in his room, and I had a planning period, and I knew he wasn't going to give this mnemonic device to his students. So I made copies of this handout, and I went and snuck into his room, and I put this paper on everybody's chair. So anyway, if you go to the store, you can buy these crackers, hi-ho crackers. And if you want to remember the derivative of a quotient where the numerator is high and the denominator is ho, right? Well, it is the denominator, ho d high, minus high d ho, all over ho ho, right? Am I right? Isn't that cute? If this is the top and ho is the bottom, ho ho is underneath ho d high minus high d ho. Love it. So that is a way you can remember the quotient rule besides du's and v's and v squares and whatever. Okay, let's try one. Find the tangents to the curve, blah, 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 at the origin. Now, firstly, you have to factor the words here. What are they asking me for? Find the tangents. That's equations. And maybe there's more than one at the origin. My algebra and my calculus will always tell me, find the tangents to the curve. That's an equation where the slope is the derivative. So step 1 is find y prime. This is a quotient that cannot be undone. So I have y, I need y prime. Step 2, what is y prime at the origin? Step 3, what is the function at the origin? Whoops. And step 4, point slope form of your tangent line. So, high over ho, find the derivative. Ho times the derivative of 4x minus high times the derivative of x squared all over x squared plus 1 squared. Notice I am not going to clean this up at all because I'm going to be plugging in 0. Plug in 0, and what do you get? So this is the slope at the origin. Next, I have to find the point at the origin. Well, hello, the origin is 0, 0, right? Now I need to write the equation. So I'm going to put 0, 0 here and the slope here. Oh, that was silly, right? This is just 4x. Crazy. Let's look at our calculator. Let's put in 4x divided by x squared plus 1. Note that denominator will never equal 0, right? So I don't have any discontinuities here. And look at the origin. Whee! Right? Remember this little trick I showed you? Second program gives me the draw. And if I want to draw the tangent line at the origin, there it is with a slope of, right. That's y equals 4x. Remember, your calculator isn't doing the quotient rule and finding the exact value, but you are allowed to consider that anything that your calculator, if your calculator's in your hands, you're allowed to consider that exact. Now, another point I want to make, if you do have a calculator, please do not do the quotient rule. You need to understand and read, and you are being tested on to see if you understand. When you have a calculator in your hands and you are asked, find the tangents, which means I need the derivative at a point. If you have a calculator in your hands, you math 8 that. There are no rubric points for doing the quotient rule, so you can do it if you want, but you A, make a mistake, and B, you have given away time the test writer has designed for you to spend on something else. So when I see students who are at the end of a test period all crunched and they're like, oh my God, it's not done, and then they leave the test and they're like, that was so unfair, it was too long. Was it too long, or did you not make the best decisions for how efficiently to do the problems? And AP and IB, and therefore we are testing that skill. It's not just content, it's problem solving. And part of problem solving is, can you do it efficiently? So when you have a calculator in your hand, don't you dare do the quotient rule. You math 8 this, right? What is the derivative of the function I put in y1 at 0? The derivative is 3.999. If you use 3.999, that's fine. If you round it to 4, that's fine, right? Either way, and then write the equation of the tangent line. Now I want to do an example where I show you, this would be without a calculator. So on the non-calculator part, what if you got that problem? Sure, you could see the quotient and you can hidey-ho that all you want. But it might be more useful if you do, in this case, remember, step 1 is to see the quotient. Step 2 is to think, can I get rid of the quotient? And look what happens. Right? I can find y. I can do algebra first, not calculus, right? This is just y, and I get 1 minus 3x to the negative 2 minus 4x to the negative, what is that, negative 4 plus 2x to the negative 5. Take the derivative of that. I don't need the quotient rule. I just need my power down rule. Derivative of a constant is 1. Careful with your subtraction. Done, right? So don't forget about algebra. Last thing I want to do is show you how AP is going to test you on the product rule and quotient rule without giving you a function. So even if you have a calculator that maybe has been programmed with the quotient rule or function rule, they're going to give you a problem like this. And again, it's probably going to be on the non-calculator part anyway. So they're going to say, here's a function that is a product. I want you to, given some information about their values and their derivative values at a particular point, find the derivative at a point. Now, I just made a big deal about you using your calculator if you were ever asked for a derivative at a point, but I can't here. I don't have the functions. You have to know that y prime is, since y prime is u times v, y prime is the first function times the derivative of the second plus the second function times the derivative of the first. And then you're just filling in values. U of 2 is 3, v prime at 2 is 2, v of 2 is 4, u prime at 2 is 1. So what is that? This is just 10, right? But you had to know the product rule. They could do the same with the quotient rule. To do the quotient rule, you have to know that this is v at 2 squared right? It is Hody high minus high d ho. And then you're just filling in values, right? I can leave you to do that. I mean, I could do the same thing with, I could ask you, given y is equal to u plus v, what is y prime? But that's pretty simple, right? That's why you like the derivative of a sum is the sum of the derivatives, right? So that's just u prime of 2 plus v prime of 2, which would be 1 plus 2, right? All right. So we will, these are your first 2 content videos, and we will do our, you have homework assignments. There's some challenging homework problems, right? Slug through them, look at the solutions, talk to each other, come see us. And you want to get down both the mechanics of the product rule and quotient rule, and you want to be wary of these AP style ones, and you want to know when you should use your calculator and when you shouldn't. Have a good one.